at a topic.
Yeah.
Here.
Should it show up on here? Ah, there it is.
We're good.
Okay, perfect. Okay, hi everybody. I'm a lecturer at the University of Cambridge, and I guess I've been working in PL for about 20 years now, which is a little hard to believe. And so what I'm going to talk to you today is about how to give a scientific talk, and to do that, I'm going to first start with, why we even bother. So the reason that we have to give talks, it fundamentally comes down to the fact that that science is a collective endeavor. So, no single human brain is large enough to understand the universe, and so we all have to go to it, work at it together. And if you want to work together, you have to talk to other people. And so, it's not the only mode of scientific communication, but it is one of them. And pretty much anyone who works in science is going to have to give some talks sometimes. And so, if you have to do it, you might as well get good at it. And so some of the, so you can think about scientific communication as like, sort of living on a spectrum. At one end, you might have individual conversations, maybe with your supervisor or a trusted teacher or mentor. And these kinds of communications are really good because, it's a dialogue and you're talking to someone and they explain something to you. And if you're confused, you can ask questions, and the person you're talking with, or you for that matter, can adjust your approach based on how the other person is responding. So that's great. And when you can do it, you should do it. But, we're computer scientists, we worry about scaling, and talking one-on-one just does not scale very well because you're talking with one other person. Sort of at the other extreme is the scientific literature. So, you have a published paper, and there's no dialogue when you're reading a paper, but it does have another key advantage, which is that, like, once you've written something down, you can go back and look at things. So if on page 15 there's some surprising claim about an equation, you can flip back and look at the equation on page 3 and figure out, like, just whether they were right or wrong. And the other thing is, papers actually scale really well. So even after I'm dead, you'll still be able to read my papers. Lectures and conference presentations and things like this, they're somewhere in the middle, and in some sense they combine the weaknesses of both approaches. So, like, I'm talking to a room of people, and the number of questions is relatively few, and you can't refer back to things that I've said because once the sound waves have died down, it's gone. It has to live in your memory or not at all. But they still have, like, a really important value because they are a lot more personal than papers. So just as an example, actually, I'll give two examples. So at the last ICFP, I was sitting next to Stephanie Wyrick, and I had mentioned to her a couple of days before that there was something about graded type theory that I didn't understand. And so while the speaker was talking, at one point she just poked me in the shoulder and said, "Hey, look at that." And she pointed at one particular rule. And then when I looked at it, all my confusions were clarified. And if you have a published paper, the paper has to explain everything. And so it's very difficult to draw your attention to things in the way that a speaker can. And secondly, we're actually just, human beings, and we have, like, sort of an emotional nature. So my favorite speaker of all is Gordon Plotkin, and objectively, he's a terrible speaker. Like, his material is very technical. His slides are stuffed full of equations, and he always overruns. And he's still absolutely my favorite speaker because he's so happy every time he speaks. Like, the joy of the work that he's doing just shines through. And at the end of the talk, I leave feeling, yes, this is how, semantics is a worthy way of spending my life. And that kind of energy and emotion really matters because the stuff we do is hard, and you need that kind of motivation and energy in order to persist at it. And that can be communicated in a way that that's difficult to do in written communication. Okay, so I said before that, like, giving talks is very difficult because you can't refer back to things that you've said very easily. Speech goes away in a way that the written word does not. And secondly, it's difficult for a large room of people to ask questions. So feel free, I'm going to tell you all, feel free to ask a question whenever you want. And most of you will take this on board, but like, you will still feel naturally shy about asking questions. And I might get 6 or 8 or a dozen questions in this talk. And that's just way less than you'll get in an individual conversation. And so the consequences of these two facts are that, like, it's often, you have to be very careful when you're giving a talk, because when you're describing something technical, even a small lapse of attention can cause a loss of comprehension. And if we know anything about human beings, it's that human attention lapses all the time. We're not like machines, we're people. And when I say human attention lapses all the time, people often have this idea that, like, it's all because of, like, phones and the internet and things like this. And that's not actually true, because human attention lapses for many, many reasons. Some of them are purely physical. The audience member might be tired or hungry or thirsty, or maybe they had a bad breakup and it's like really messing with their head. Or, maybe the talk is just too hard and, like, it assumes all kinds of background information you don't have and you can't make heads or tails of it. Or, the opposite problem happens also. Like, if the talk is too easy and your audience, feels like they understand everything already, they're like, okay, this listening here is a sort of a waste of my time and I'm not going to pay any attention. And so another thing that happens is, when you're talking about complicated technical material, it takes a significant investment of mental energy in order to be able to follow the talk. And if you don't really communicate a solid motivation to persuade your audience to invest that energy, then they're not going to. So if your motive is unclear, then you can't really explain difficult material to people. So the point is that, like, when someone pulls out a laptop or looks at their phone, this is a symptom rather than a cause. And so that means that we need to, focus on managing attention as, like, sort of the key difficulty of like, scientific of a scientific talk. And so how do we manage human attention? So, people have been doing it for literally tens of thousands of years, probably long before, even like fabric was invented or something, like maybe hundreds of thousands of years. And the way they do this, or the way that people hold each other's attention during conversations, is by telling a story. So your story has, like, some sort of question which raises some sort of situation which raises a question in the reader's mind. So if I'm telling my daughter a bedtime story, what she asks is, what happens next? And then when I answer the question, so I say, oh yes, the little girl escaped from the bear by falling into a big hole, she has another question, which is, okay, now what happens to the girl? Does she get out of the hole? And so by asking questions whose answers raise further questions, you can hold your audience's attention. So you can use narrative to sort of help people follow your talk. And what I mean is, you don't need to be Vladimir Nabokov or Jane Austen or somebody. Like, even though Nabokov did publish scientific papers, he loved butterflies and he published in entomology journals. But, it wasn't florid, beautiful prose in his scientific papers. He was describing a butterfly. And the reason is that, like, the way that the narrative structure that you give in a scientific talk, it doesn't need to be very complicated. So you only need a very simple narrative structure. So I'll give an example for, like, the sort of talks we'll see in POPL. I did 20 minutes here, but I think, is it 15 minutes this POPL? I can't remember. So it's 15, 20 minutes. Like, this is a typical conference talk. And so the way that you want to structure it is you want to open by giving some motivation for what you're doing. So you've done some complicated thing and you want to tell the world about it so that other people understand it, and, like, sort of the understanding waterline of humanity is raised. So you want to explain what are the problems that you're trying to solve and why is it important to solve this problem. And so, that will hopefully get your audience to think, yes, this is an important problem, it's worth solving, now I want to know how. And then what you want to do is you want to give like sort of a kind of a roadmap to solving the problem. So this is going to be not a specific detail right away, but just a high-level overview. And so you want to explain what you did in general, and like, you know, what ideas underlie this approach. And you want to have like a high-level roadmap because you know, when you get into the technical material, you need to you need to like justify to your audience, yes, I see that there's a plausible approach. It's worth devoting the attention to it, and that's in the rest of the talk. But also, anytime you do a piece of scientific research, you know, you're describing like what took you like a year or 2 years of work to do, and you had lots of ideas during that time. And in your talk, you only have time to explain one, maybe two things, and you want to like, you know, get that penumbra of stuff in your audience's mind so that they can say, yes, the thing that you're doing makes sense, and there's also more stuff for them to learn in the rest of the paper. And so then after actually explaining your, like one of the technical ideas in your paper, you can close with a conclusion where you contextualize what you've done and relate it back to the problem. So you can see how the thing that was done connects back to the original motivation. And then you can let your audience ask questions if they haven't been already. Okay, so let me focus on motivation. This is actually going to be the biggest part of my talk because it's actually one of the most important parts of the talk because like, you know, even sitting through a talk is an investment in your audience's attention, and part of what you're trying to do is you're trying to communicate to them that, like, you know, this little bit of attention is for them to judge whether they should devote much more attention by like actually giving your paper a close read. And so in order to figure that out, you have to explain to them the problem, the motivation. And so fundamentally, it comes down to answering two questions. So like, you know, what is the problem? And second, why should anyone care? Like, you know, it's easy to make up questions. It's more difficult to come up with the reason why you should care about the solution. But you have to answer both of these questions in the audience's mind before they'll be convinced that it's worth the effort of paying attention to the speaker. And so I mean, what I mean here is like really your audience is giving you a gift. They're giving you the gift of attention, and you need to demonstrate to them that, you know, their trust in you is not misplaced. And so there's sort of two main styles of motivation in scientific talks. And, you know, you can think of this as like, you know, the top-down or engineering view, where you say, here's a problem that obviously needs to be solved. How do we solve it? And then there's also a contrasting style, which is like the bottom-up, or what you might call scientific style, where you say, here are some puzzling observations, and there's some sort of tantalizing connection between them. How can we understand this relationship better? And so what I'm going to do is I'm going to go through two different talks and sort of give you an example of how this kind of motivation can work. So for the top-down motivation, like the key things you need to do is you need to really lay out the problem and make clear why this problem has to be solved. And so once the audience has bought into the question, bought into your question and want to know the answer, then they'll be ready to join you on the search for the solution. And so, you know, there's also like, when you try this style of motivation, there's sort of two dangers. You might fail to articulate the problem, or you might even just take too long to get to the problem. And so let me give you an example. So this is a paper that my co-author, Jana Dunfield, presented with me in POPL 2019. And so it has a very long title, but it's fundamentally about type inference. So I'm going to tell you a little bit about it so that you can understand like the shape of one of these motivation sections. I'm not claiming that this is a perfect talk, but like I want to show you a real talk, not necessarily the ideal. And so what I did was I said, okay, I'm going to talk about a fancy type system feature called generalized algebraic data types. And what are these data types? Well, they're like a normal data type in a functional language, except that you can add additional information to your type. So here we have vector, this is sort of like the hello world of generalized algebraic data types. We have vectors, which are length indexed lists. And so if you look at the type of nil, what you see is that this is a, a vector of length 0 right here. And so that's the type of nil. And the type of cons says that if you give me a head element and a vector of length n, the result is a vector of length n plus 1. And so that looks very obvious, but it lets you write some really cool programs. So for instance, here is a very small but cool program, and this is the head function. So if you're given a non-empty list, it'll give you an element. And it'll do so by giving you the first element in that list. And so you're saying, okay, that's fine, but the thing that makes this really cool is that this is a whole program that will never crash. It's a complete set of pattern matches. You don't need to match on the nil case because it's impossible. And so this, and then you can, the normal functional programs on lists are going to do things like their types will give you additional information. So like map is going to preserve the length of the list. So if you give it a list of length n, mapping a function over it will produce another list of length n. And other functions like filter, you can say, well, okay, when you filter something, you give it a predicate and a list of length n, and because the filter function can drop some elements, you're going to get out a possibly smaller list. And so you can see that this is a really cool feature to program with, and now that I've explained what the feature is, I can explain what the problem is. And the problem here is that implementing fancy type systems is very, very hard. And you need a lot of specialized expertise to do it. And if you have that expertise, you are probably on a first name basis with one of 3 people. And the point here is now here is the problem. As scientists, we want information to be universally available, and we have this really cool thing which is sort of transmitted master apprentice style. So that's a problem, and it needs to be solved. And so you can see that the motivation here is top down. So here is a problem, we really need to solve it. And so now I'll give you an example of a bottom-up motivation where we start with some fascinating observations, and then we observe some surprising connection, and now we're motivated to understand why this connection exists. And so the dangers here are sort of the opposite of the ones for the top-down exposition. And so the first danger is that a collection of random facts is just going to be boring. Why am I getting hit with random facts for a long time? And the second second problem is a little bit more subtle. And so the second problem is sometimes for super experts, the connection is immediately obvious, but if you're less expert, the connection might be opaque. And you're like, okay, well, these people are super excited, but I don't understand why. Okay, so now I'm going to give you my absolute favorite example of one of these kinds of bottom-up motivations. This was a talk given about 10 years ago by Noam Zeilberger, who's a researcher in Paris. And what he did was he said, I'm going to show you a connection between the lambda calculus and maps. And so what does that mean? And so what he did was he said, okay, what I'm going to do is I'm going to look at a certain class of the lambda calculus. I'm going to count the number of lambda calculus terms that have one free variable and are linear. And so if you have one free variable, if you're allowed to have one variable, one of which is free, there's exactly one such term. And if you move up to 2 variables, one of which is free, there are 2 such terms. And if you go up to 3 variables, there are 9 such terms. And here he's enumerating each of these variables. And then he says, and if I go to 4 free variables, then I get 54 such terms. And so you can see here that this is, at first, a really eccentric thing to do. He's picked some strange lambda calculus, and now he's not even running these programs. He's just counting them. And so, this is a peculiar thing to do. And then he says, okay, well, I have been counting these terms and I have a sequence of integers. Here's what I'm going to do. I am going to stick it into the online encyclopedia of integer sequences. And we're going to see what it tells us. And what is the sequence that starts with 1, 2, 9, 54, and then he wrote a computer program to count these terms, 378, 2916. What is this sequence? And the OEIS says, this is the number of router planar maps with n edges, or n vertices. And so what are those? Well, let's draw some pictures. So a rooted planar map was a thing invented by Bill Tutte, who's like one of the most famous graph theorists of all time. And he invented it in the 1960s, and what it is it's a graph that you can draw on the plane without any edges crossing, and where one of the edges is distinguished. That's the one with the arrow. So you have a planar map here. And then if you pick out one of the edges as special, then it's a rooted planar map. And he wrote a paper on how you can count these things, which is where this series on the previous page came from. And so then he said, okay, let's take a look at these things. And so here's the rooted planar map with one vertex, then and then 2, and then when you go up to 3, you get 9, and then when you go up to 4, you get 54, and now we have established that there's this shocking connection. So you have the lambda calculus, or the linear lambda calculus, which is a thing people know about and use for various purposes. Like if you've programmed in Rust, you've programmed in a basically linearly typed language. And now here is Bill Tutte, decades before the linear lambda calculus has been invented, and he's come up with something that's isomorphic to the linear lambda calculus. And at first glance, there's no connection between graph theory and lambda calculus, and yet here it is. And so now what Noam has done is he has established a relationship between two disparate things. And now, if you have a mathematical soul at all, you're thinking, what the heck is going on? I have to know what's happening here. So in other words, the point of a motivation of the motivation of your talk is to identify a problem and convince your audience that something interesting is about to happen, or the answer to this question is going to be interesting. Okay, so now you've motivated your talk, and you've convinced your audience that there is a problem that they have to know the answer to, or they'll be irritated with you. And you have to explain what you did. And what you want to do is you want to give an overview of what you did, so that the audience understands the landscape of your solution, and then you want to identify one particular key idea that you're going to go into more detail with. And so if your motivation section has been successful, they'll be intrigued with your problem and they want to know the answer. And so at this point, you have to start telling them what the solution is. But the thing is, you can't tell them everything. Like I said, a paper typically describes a year to 2 years of work, and that can't really be summarized completely in a 20-minute talk. So you need to tell them something, and should tell them one thing. And the reason why it's 1 is because it can't be 0, because you have successfully convinced people that the solution to this problem is interesting. And if you fail to tell them anything, they're going to be mad at you. They're like, okay, you've convinced me that I want to know how to do type inference, and now you've told me nothing about how to solve the problem. I'm mad at you. The other mistake that people make is that a typical advance is going to require several innovations, and if you try to explain all of them, your audience will get confused. Because we're human beings, we learn things a bit at a time, and if you get hit with a wall of ideas, then you can't integrate one idea before the next one comes, and you end up assimilating nothing at all. And so so if you try to explain too much, your audience will be confused and they won't be able to take anything away from your talk, just like if you didn't tell them anything. So tell them something, but not too much. And so here is an example contribution slide. This is from my 2019 talk. And I said, okay, and so you can see up there at the top, I set out the question, can we find a type system for GADTs that fits in one paper and that you can read and then implement? And I said, oh yes, of course. What you need to do is you need to use the Curry-Howard correspondence and then add a sprinkling of structural proof theory, and you'll be able to get the type inference algorithm that you want. And then a little bit later, I laid out all the different pieces that went into the solution, and I highlighted a couple that were going to be in the talk. And what I want to do here is to say, actually, this contribution slide isn't perfect. I combined the big question with the technical approach, and when it would have been better to separate them, to give the audience some time to assimilate what's going on. And there are no examples right there either, because people learn generalizations from concrete examples. But it does the job. Humans are finite. Conference sessions are also finite, and because of this finiteness, there's always a tension between can I explain this thing better? And if I do, then the next thing is explained less well. So you have to pick your battles a little bit. And you shouldn't feel worried if you're thinking, oh, this isn't perfect, my audience will hate me. Actually, pretty much everyone in the audience wants you to succeed. They want to sit and hear something interesting, and they also understand that telling people how to do things is sort of an inherently stressful thing. So you should presume the goodwill of your audience, but you shouldn't beat it up a little bit. Okay, so now let's talk about how you should explain your key idea. And what you want to do is you want to explain something sort of interestingly technical in enough detail that the audience can get something from it. So ideally, you want them to understand something well enough that when they go and read your paper, they're like, aha, this makes total sense. And all those things I was confused about in the talk, they're explained right here. And I have the high-level structure in my head from the talk, and so this makes the paper itself much easier to read. But once you start explaining something really technical, you're in danger. And the danger is that lapses of attention damage comprehension, and human attention lapses all the time. Okay, so let's pause for a moment to look at a cat. This is not my cat. This is my brother's cat. And it paused to relax. Its attention has lapsed. And now, after relaxing a little bit, let's come back and think about how we can explain our technical idea. And so, because we are computer programmers, what we can do is we can say, we have a big problem. Let's break it up into smaller problems and solve them individually. We can appeal to recursion. And so what you want to do is you want to divide your big idea, the thing you want to explain in detail, into smaller pieces, and you treat each segment of your exposition as a tiny little talk in its own right. And what you want to do is you want to start with a motivation, explain the idea sort of contextually, actually explain it, and then close with the conclusion. And so the thing that's going to save your audience from losing attention is that your motivation and conclusion, for each segment, are going to link together. So you're repeating what you've said so that anyone who's zoned out for a second can be brought back up to speed. And for the people who didn't zone out, it's actually helpful for them to understand why the thing they just understood is actually a useful thing to do. And so you're reminding your audience of what you did and why, so that they can stay with you as you speak. All right, so now what you want to do, so I'll give you a tiny little talk segment. So this wasn't supposed to be a technical talk, but you're going to get some anyway. And so what I explained in one piece of the type inference algorithm I explained was something about existential types. And if you don't know what they are, I'm about to explain it to you. So what I did was I said, okay, we have in logic, universal and existential quantification. And when you're defining these fancy GADT data type, you turn out to need existential quantification in order to express these GADT constraints properly. And so, look, there's an existential type, and it lets you do things like information hiding. So a list of unknown length is the same as saying, oh, there exists an n such that I have a vector of length n. And these existential types are actually really important for programming with GADTs. So for instance, in the filter function, what we're going to do is we say, okay, for a list of any length n, the result of filtering is going to be a list of some length k. And so now we have a type that has both for all and exists in it. And historically, people, when they've seen type systems with both of these features, they've run away because it's really hard. And so now I have set up the problem here. I briefly explained what the issue was, and I explained, what the problem is here. And so here, I want to point out here. So I want to say, since I've gone into the technical section of the talk here, the reminder of what existential types here was relatively brief. So, a type theorist will say, yes, I understand this. But if you're not a type theorist, you'll probably be scratching your head. And in the technical part of your talk, it's a little bit okay to do that. Ideally you want everyone to understand everything, but as I said, it's always a compromise. Okay, and so now we have established what the problem is. This is hard, and now we're going to explain that it's actually harder than you thought, because when you have a fancy type system with quantifiers, we also want type inference. So if we have a two-string function and a map function and a vector, we want to write map two-string over x's. We don't want to write something where each of those quantifiers gets explicitly instantiated by the programmer, because then half the program has turned from actual code that does things into type annotations. And so now we need to model type inference using this feature called subtyping, where we say, okay, we have this polymorphic function, but we want to use it as a concrete type, and we'll model that with subtyping. Again, this is an idea that is relatively familiar to experts, and now they're being reminded of it. So we're in sort of the weeds of the talk here. So the reminders of what the problem is can be just a little bit terse, because you have only so many minutes. And so what I did was I said, okay, well, look here, this is the normal thing in type inference. And then when you add existential types, it's the similar, except everything gets dualized. And then when you have a language with both of these things, you have both the for all rules and the exist rules. And this is the place where you're going to have some problems. It's easy to stick both sets of rules in the system, but it creates a problem. And the problem is that the order that you can use these rules in becomes ambiguous. So, you can, if you're checking that for all A is a subtype of B, then there's two possible ways of doing it, and neither one is strictly better than the other. So you can guess the for all first and then the exists, or the other way around. And now we have a problem, because when you have two choices, an algorithm may have to try both. And this has created backtracking in your algorithm, because if you have multiple places where these quantifiers can occur, you have multiple places where backtracking can happen. And this would make your algorithm exponential time. And nobody would be happy with you if you did that. And so now I've explained what the problem is and said, okay, now exponential time is bad. I've created the motivation for wanting a solution. And now I can say, okay, well, now here's my high-level exposition. Again, it's going to be fairly technical, because we're in the actually explain technical bits of your talk. And I say, oh yes, there's this thing called polarization or focusing, and it divides everything into positives and negatives. And now what we could or values and computations. And with this separation, what you can do is take the old ambiguous rules and you can make them unambiguous by separating it into two relations. And you only use one set of rules at a time, and they can never interfere with each other. And so we've eliminated the ambiguity, and we've solved the problem of making the subtyping relation syntax directed. So exponential time is gone now. So what you can see here is that the explanation of this one feature was actually a micro talk. So the key idea was divided into a couple of pieces, and I treated each piece as like a tiny talk in its own right. And there was a beginning, a middle, a motivation, some overview, and then like a solution, and then like there was a bit of contextualization at the end to say, why has this actually helped? Okay, so now you have fully explained a deep technical idea to your audience, and now everyone in the audience is a lot smarter than before. So you're done, right? Well, no, because you can think of what's happened in the talk so far as like you've climbed up to the top of the diving board and you've jumped into the ocean, and now as you go into more and more technical depth, you've gone deeper and deeper into the water. And now you need to come up for air again. And so the goal in your conclusion is you want to contextualize the technical stuff that you've did so that the audience understands what's happened, and then you want to remind them that there's more stuff in the paper, more things that you need to understand in order to actually solve the problem, and you want to set the audience up so that they can successfully ask you questions once the talk is done. Okay, so what does contextualization mean? So what this means is that you've explained something hard, and what you want to do is you want to explain, okay, why did I do this, and how does this solve the big picture problem that I set up at the beginning of the talk? So let me show you how I did this. So what I did was, in my talk was I gave one slide where I said, okay, you've been hit with a wall of type theory, and many of your heads are hurting. So was this too much? And I said, okay, well, the goal of our work was to build a type system that you could read one paper and implement. And here's somebody who I've never met, who just emailed me and said, hey, I read your draft and I implemented it. And he was an undergraduate in India. And so now this answers the question that I set up at the beginning, which is it possible to turn this feature into something that doesn't require like transmission via a master-apprentice chain? And so now the reason why we went into this technical detail is justified in terms of like the higher level outcomes. And as I said before, like, any paper is always going to have more stuff than fits in a talk. But if you've successfully explained something interesting to the audience, they're excited. They're like, yes, I can see that this thing that you explained is definitely going to help solve the problem. But, it's also sort of clear that it's not enough by itself. And so what you want to do is you want to tell the audience what's in the rest of the paper so that, they'll understand whether it's worth their time to invest in that. And the other thing you want to do is you want to actually summarize your talk on the last slide. And this is because people can't flip back to the previous part of your talk. So if they have a question, as they're watching the talk, some questions might arise in their mind, and then as time passes, like the question is washed away by like your sparkling words. And so if you put a summary slide at the end, then that'll remind them what was in the talk, so that they can ask their questions to you. So in other words, never ever end on a slide like this or like this. What you want to do is you want to break the rules of presentations and hit them with lots of text, because the text is there to help the audience remember what you said so that they can remember what confused them and they can ask you questions about it. Okay, and so now let's conclude this talk. And I'm going to hit you with that wall of text. So, remember that a talk is about managing attention, and that you want to motivate the problem so that they want to know the answer, and then you want to give them the lay of the land, and then explain the technical idea by breaking it into tiny little talks that repeatedly motivate the thing that you're doing and connect it back to the larger questions. And then when you finish the talk, you want to put them in a place where they can ask you questions and remember what you did. And now I should be able, let's see if I've got time to take any questions. Perfect, I do have time to ask you questions. So, I'm happy to take questions now.
Let's all thank Neel. So what is the connection between the graphs and the linear lambda calculus?
So what is the connection between the graphs and the linear lambda calculus? So it turns out that the you can think of like the rooted edge as like being equivalent to the free variable, and Noam has a long series of papers going into more and more detail about this, and they're really cool. And it even turns out to have some neat applications, because people doing synthesis often want to enumerate programs in order to learn things. And hey, look, combinatorists have spent like maybe hundreds of years working out how to enumerate things. So it's really quite slick.
Thank you for the talk. It was really good. I was wondering, when you gave the overview of all this at the beginning, you made a little, you gave the times, and I guess it's an approximation of the time it should take. Would you say that it generalized to talks that are longer or not? Like proportionally?
Yeah, so the thing to remember is that the times I gave are actually a rule of thumb. Sometimes, the reason why a problem is interesting is like is going to be really obvious to your audience. So like, if you solve P versus NP, then you don't really need to spend a lot of time explaining why this is important. But on the other hand, it is really worth spending a considerable fraction of your time, explaining the high-level problem and what your motivation is, because the number of people who understand the really deep technical parts is not going to be very high. Because if you look at the POPL audience, there's going to be people doing like category theory and separation logic and proof assistance and static analysis and finite model theory, and anyone who's an expert in one of those will find the next thing over to be super hard. And so so the opening of your talk is your chance to teach people who aren't like super experts in your area something interesting as well. So it is actually worth spending a good deal of time on that.
Okay, so you're saying for a 1 hour talk, it's also worth taking a good chunk of that doing the introduction.
Yeah, that's right. Because longer talks are often things like seminar talks or keynotes, where you have a bigger audience of people who are often not experts. If you're visiting a research group and like your closest collaborator and his 4 students are there, then you can get straight into the technical stuff. But like typically people from all over the department or a whole conference are going to be there, and is worth explaining stuff to them.
All right, let us thank Neel again.